Good afternoon, everyone, and welcome to the CPCI 5th edition Design Manual Chapter 3 webinar presentation. My name is Ariane Sabourin. I am the Marketing Manager for CPCI. Thank you for taking the time out of your busy schedules to join us for today's webinar session. Our presenter today is Medhat Ghabrial. He's the editor of Chapter 3 of the CPCI 5th edition Design Manual. Medhat's presentation will focus on the major changes and additions to Chapter 3, Design of Elements. Before we get started, we'd like to acknowledge the support of our CPCI member sponsors of the Design Manual webinar series. Thank you to the following companies: BASF, JVI Inc., MCM Industrial Consultants, and Ultraspan. It is this type of support from our members that assures CPCI can continue to develop and deliver high-quality programs and services such as this, and to build on our body of knowledge for the architecture, engineering, and construction industry. So without further ado, I will now turn it over to Medhat for the presentation. Thank you.
Good afternoon, ladies and gentlemen. We're going to go through a very lengthy chapter, trying to do it as fast as we can because the hour is very short, actually 50 minutes. Usually I will start as usual by counting the blessing of Precast, the litany of how Precast is wonderful. We are talking about, of course, construction speeds and the fact that plant control quality increase F'(C), 5C from 0.65 to 0.7. And we have fire resistance, durability, of course, and the prestressing will allow a huge advantage in the span to depth ratio. Next, please. Also, I want to add something here that's not on the screen. Prestressing usually decrease the possibility of cracking, of course, by definition, and therefore the maintenance of a building would be cost of maintenance would be reduced immensely if we have prestressed element there. Plant control precast usually gives the architect a huge advantage of fulfilling his dreams of coloring and shapes and curves and what have you that they cannot be achieved by regular cast-in-place concrete. And the last two things that I like to also add to is the fact that precast is much better element when it comes to thermal and acoustical control of buildings. And of course, because we live in very cold country, Precast is major blessing because we can construct, erect, and produce 12 months a year, opposed to any other material that we can use in construction. Next. In the next 50 minutes, we'll try to run real fast on the subjects of all the issues that covered in that chapter. We go by first we can see what happened to the load resistance factor, change a little bit, and we'll go through the main stuff: the Flexural Design at optimum limit state, Serviceability Limit State, touch camber and deflection, and the big item is the shear and torsion because it keeps changing all the time. Every time it when sequence 3 issued a new version, they have some tweaking there. And the compression members will go through them fast, but we'll try to talk a little bit more elaborate about piles. Then we'll go to stripping and handling and erection, obviously as design issues, as analysis issue. And the one that's now increasing in leaps and bounds are the multi-wise members. And the last but not least, we're going to say that in this chapter there is a post-tensioning section, but we'll not talk much about it anyway. The load and resistance factors, this is what we have right now, which follows NBC 15. If you are familiar with these numbers, you'll notice that cases 2, 3, and 4 have changed immensely compared to the ones we had before in NBC 05. And it moved a little bit in the direction of conservatism as opposed to being more liberal. So those 7 cases that we usually design for, and notice that 2, 3, and 4 have changed. And as for the importance factor and material, But porous factor stayed the same. I want to emphasize the fact that the factor for phi, again, for precast concrete certified to CSA 23.4, phi sub C is 0.7 as opposed to 0.65, which is a decent advantage for precast. But the rest of the factors are the same as per the old manual. Okay, nice picture of a beam, a pre-stressed precast beam. As an introduction to what we're going to say right now, we're going to go through real fast now with the basic formulation of a beam under flexure. This formula here is the standard generalized formula of a beam section under both prestressing strands and mild steel reinforcements. And the formula at the bottom is the standard equation to calculate the value of A, the compression block on top. We'll take this and apply it to different cases and we'll try to see a couple of example solves, but it's not going to be that much of a time consumed here. We have some, in the book, we have some design tables to help you go through the design of beams under flexure. These tables, these formulae here for non-prestressed sections, if you're designing or analyzing, and I noticed that there is a typo here in analysis. First line, AP here should be A sub S, not A sub P. So that's a typo that's still sitting there. But other than that, these are the formulae we use for design. That's the steps we use when we use the tables that we have in the book for non-prestressed concrete elements under flexure. That's a very fast example of a beam with a ledge that has 1, 2, 3, 4, 5, 6, 7, 8 bars. We first calculated the case of R from the fact that we already have the M sub F, and then calculated omega, then AS, which checked if AS is this or more than the minimum. We found out obviously it's more than the minimum, so we can use 725 rate for 100 bar. This is an example from the book, following the table that we have in the book, and following CSA A23.3. And this here is a stadia, another example that I like to emphasize a little bit on, because we always use those stadium elements everywhere now in precast concrete industry. The problem with the stadia element is it's not symmetrical, so we need to do some analysis first, some math. We need to calculate the major axis of inertia, minimum and maximum, using the old formulae of minimum and maximum inertia. We have to calculate I sub xy, ix and iy, calculate the theta, and then after that we'll find out that every strand in the stadia will have different depths for the section that will be calculated using the axis of inertia that represent the minimum inertia of the section. So every one of these strands will have different depths, and therefore the calculation of the section capacity would be the summation of each and every strand strengths using the theta of the minimum inertia axis, which happened to be 21.9. Once you go through that, we calculate the basic stuff. We found out that the section is safe, obviously. Next, please. It's a picture of a nice stadia, a real life stadia. Essentially, those stadia can be two tier, 3 tier, 4 tier stadia, and the more tiers we have, the better quality we get in terms of economy. But obviously, the negative side is it's harder to analyze, harder to produce, and harder to ship. but the reason now is we say that the more tiers, the better as a whole. These are the formulae that we used for the stadia element because it's a pre-stressed precast. Therefore, these formulae here pertain to pre-stress element. That's why we have the AP here as opposed to AS. And these are the introduction formulae for the table that we have in the book. And another fast example of a section using the same tables, but this time it's not a stadia, it's a typical rectangular section. And basically the same thing, we calculate case of R, and then you calculate omega PU, and then after that you find out how many area of pre-stressing strands we need, and we supply it. And so that the table that we have in the book are very handy for simple design of pre-stressed and non-pre-stressed flexure members at ultimate limit states. Now we go to the serviceability limit state. A problem here that we usually face is the fact that once for a precaster to produce a beam and strip it, handle, shape it, and erect it, and under service limit state loads, usually it creates cracks, and in our industry, cracks are something that we need to be very concerned with and controlling it. So essentially, in serviceability limit state, we need to check the crack width using the old formula here that calculate the Z value. And if you can see that, depending on the location of the element in the structure, are they exposed or not exposed? Are they interior or not interior? Are they pre-stressed or not pre-stressed? Are the critical appearance, like in architectural precast, or interior exposure or exterior exposure, exposed to the weather and the elements? So for each and every function and exposure type, there is certain value for Z defined by the codes, and for that there is a certain value for depth width of crack defined as well. So essentially, once we know what kind of element we have, what kind of exposure we have, we calculate Z for that particular exposure using the area A here, which is the area surrounding the pre-stressed strands or the reinforcements. And from there, we calculate the needed reinforcement, assuming that Fs is 0.6 Fy. That's an assumption that came out handy. That the allowed stress at serviceability limit state controlling cracks is 0.6 Fy. Once you calculate the needed reinforcement, we compare this to the reinforcement that we obtained from ultimate limit states. Sometimes this reinforcement, in many cases, is the government reinforcement, not the one that came from the ultimate limit state, and therefore this is the one that will be provided to the section or to the elements, not the one that's provided, or not the one that came from the calculations that we just did before. So in this case, we have to do it twice. For pre-stressed element design, obviously, one thing that we always check are the stresses of the concretes, top and bottom fibers at release, at erection, and also at under full loads. And the codes spells out exactly what kind of stresses we cannot exceed in each and every case. And these are the values that need to be followed and obeyed all the time. Notice that the tension at end simply supported element is this value here, 0.5 lambda square root F prime C, but tension except at the end is 0.25 lambda F square root F prime CI. And these values here are essentially, in many cases, are the values that will probably control the final design of the section, not the ultimate limit state. So we have three things to check. We have the ultimate limit state, we have the the service limit state at stripping, at the transfer, and at the final serviceability conditions. And then it's a jogging act, depending how we work your numbers around those three stages. And usually, in many cases, the ultimate limit state for pre-stressed concrete, not usually, in most cases or majority of cases, is not the case that will control the final design. Again, this is this is the list of the rest of the limitation. These are for after losses, compression due to total loads, tension of the pre-compressed tensile zone, and now this for pre-stressing strands themselves, we cannot have more than 0.8 FPU as the pulling stress. I won't even go to 0.8. We usually go to 0.75 or 0.7 at the most, but it cannot be exceeding the 0.8 value. We assume in this analysis that the strain is linear, so basically we can add up simply the cases of load as if we are adding up linear to linear to linear to linear P over A. This is here the pre-stressing diagram, moment diagram. This is the moment due to moment, the diagram due to moment, and these are the final one. We add them up as we go, case by case by case. Essentially, the same CDA unit that we've been doing for 200 years now, the same section again and again and again. This time we're checking the stresses at the stadia on different spots, because the stadia is basically not symmetrical. So we have at least 6 or 7 points in the profile that need to be checked. So here we are checking 1 point as an example, finding out exactly. We calculate the moment MX and MY, because now we have two components of the moments, because of we're calculating everything at theta equal to 21.5 degrees, I believe. So we have value for MX and value for MY as component of M, which is the total moment acting on the section. And once we calculate MX and MY, we calculate the stresses, PA over AG, plus these are the stresses due to pre-stressing, EY and EX, then MX and MY, plus or minus depending on where you are. Then you calculate the total stress, compare it to the allowable by codes, and then after that you keep going with another step, another point, another point, another point. Okay. I will show exactly what I mean, but see, this here is the points that need to be checked. 1, 2, 3, 4, 5, 6, 7. Each one of them will have different coordinates, and will have different EX and EY, and therefore each and every one of them will have different stresses, final stresses, and also at release and also at service. So that's why a situation like that will take quite a bit of time to finalize, to finish. And this only two tier stadia. If it's 3 tiers or 4 tiers, is becoming really pain, and the designer in this case will spend a huge amount of time just designing one stadia unit like this. But the same principle anyway. And here's another picture of another case of another stadium. This is arena in New York, and all the elements here were 2 and 3 tiers. Obviously, one item that we need also to look at all the time when we design is what's the difference between the initial stress at release and the final stress in pre-stressing strands at service. We find out that there are sources of losses of the pre-stressing force. We all know them. The first one here, it happened once we transfer, This one is only related to post tension, the friction between the tendons and the wall of the duct itself. But 3, 4, 5, and 6 are common to all pre-stressing elements. Pre-stress element, I mean, the elastic shortening, of course, of the components, the concrete elastic shortening, creep of concrete, shrink of concrete, and then the tendon itself, after a while, start to relax a little bit. That's why we like all the time to use what you call low relax strands as opposed to regular type strands. There are two methods of calculating the losses: the fast one and the detailed one. We'll go real fast here using the fast one. The fast one essentially, the page is not shown here. It's essentially, if you go to this line here, it will tell you the whole thing. The fast one will say that the total pre-stressing losses is this value here, plus 16.3 FCO plus 5.4 FCI, where FCO is this of the stress of the concrete at the strand level at release, and this here of the stress of concrete at strand level under on weights and dead loads. Once we reach this line here, calculate these two values and add them up, we find out that this is the total losses. Notice if you go up here, we find out that essentially where the original stresses? Yeah, 1660 kilonewton. This is what we started with, and after the release, we have a little bit of losses that went down to 1536 due to the anchor setting, and then the long term are referred to by these two components, and therefore by adding up all of them, we'll end up with 241 megapascal, which is essentially it's not shown here on the screen, unfortunately. Like we turn that to kilonewton and find out that it's about 15% total losses at service from the original value. Now we come to the partially pre-stressed concrete as a concept. It's sometimes we know that the live load is not happening in real life. Therefore, it's not a bad idea to assume that the section, pre-stress section, under full load, if it ever occurs, can show a little bit of extra stress over and above the allowed by code for the tensile face of the section at the bottom. And by doing that, we allow cracks in the pre-stress section more than what is allows stresses beyond the allowed in the code, and therefore allowing some cracks. And these cracks essentially have to be controlled again. Same thing that when we talked about 5-10 minutes ago, when we said about controlling cracks with the size of crack and the type of exposure. But the partially pre-stressed concrete is a good feature. It's not a bad thing to use it all the time, or not all the time, at least most of the cases, because it has advantages. It has major advantages. It reduces the number of strands in a section. It reduces the camber. It reduces the pre-stressing forces. Therefore, it reduces the losses, and also if you are post-tensioning, usually you have some cracks at the end due to the post-tensioning force. That will reduce the post-tensioning cracking at the end zones. And on top of that, it's economical. It's a very good. It's economically advantageous practice, because by providing non-pre-stress reinforcement in the section, you're reducing the cost and also reducing that congestion. And in reality, almost everybody is now in real life try to use partially pre-stressed concrete in everyday practice, as opposed to the totally pre-stressed concrete. Unless you have some kind of a condition that you cannot run away from, maybe the live load is definitely going to be achieved, like snow load, for instance, that we know that's going to happen. And also if it's the cracking conditions are not desirable at all, if the exposure is critical, if it's architectural feature that cannot be marrying a crack under one way or under any condition, then therefore you check the section as a fully pre-stressed concrete, not partially pre-stressed concrete. But in reality, it's not a bad idea to use partially pre-stressed concrete. Essentially, you allow that the value defined by codes for service limited state tensile stresses to be exceeded, sometimes to double the value, and therefore reduce the amount of pre-stressing force that need to be taken into account, as long as the ultimate limit state is checked finally, fine, and also the crack control issue is kept in check. We know that strands in a beam or in a slab need some room to be transferred. It's actually transferred the force in the strand by bond to the concrete, and that length that needed to be provided to the strand to transfer its force is usually 50 times the nominal diameter of the strand as a rule of thumb. But of course, the development length, which is the length needed to develop the whole full strength of the strand, not only transfer the value, is much longer than that. It's usually double that much. And the codes now gives us this formula here to calculate the development length of a strand. So there are two different subjects here. Transfer length is 50 times the nominal diameter. Development length is usually almost double that much, and it needs to be checked using this formula here. That will be looked into it very elaborately in this nice example here. We have a cantilever beam, 2-meter cantilever and 6-meter span. We have the section that essentially designed or tailor-made to fit this condition. We have top strands and bottom strands. The top strands are there to take care of the cantilever portion, and the bottom strands are there to take care of the span portion. But obviously, the top strands cannot be desirable in the span portion because it will take away the capacity of the section here. Therefore, we like to have at least two of them, these two unbonded in the span portion. Same thing with the cantilever portion. The bottom strands do not need to continue all the way to the end. The 4 of them are debonded at the bottom in the cantilever portion. The two of the top strands are debonded in the span portion. So we have 4 top, 7 bottom, and we calculate the standard section values, YT, YB, ST, SB, etc., and they will calculate the eccentricity. And this here tells you what I just said 5 seconds ago. And once we achieve this, to arrive at this agreement, then we can calculate the stresses, initial stresses at different sections, and also the final stresses. Essentially, this here is the strand elevation, the strand value of stresses as per our explanation that we had before. To the top strand developed and is 650 millimeter, which is 50 times the diameter almost, and then after that, once it's debonded, it takes double as much length for a debonded strands to develop, and therefore this here represents the behavior elevation of the top strand that has debonded in the span. This one here represents the top strand that has not debonded, which is continuous all the way, and therefore it transferred here. It transferred here, and it maintained the stress all the way across. The bottom strand, that was the 4 of them that were debonded, developed here. Sorry, they transferred here, then kept going at the maximum transfer force, and then debonded to 0 at the cantilever portion. And the one that continuous is continuous all the way. And then once we arrived at this, we can calculate the stresses top and bottom at different section. Essentially, this is the way it's usually done for a cantilever beam like this. And next again, if you don't mind, these are stresses of the top stresses, top fiber compression, and this is bottom fiber compression as accumulated, taken section after section after section after section. And this graph here at the bottom is this for the same example. These are the final, not the final, the service limit state stresses for each and every strands type, the bonded and the non-bonded top and bottom. Okay, this here was this a new example we added this time. Actually, it was done differently last time, but we decided to enhance it a little bit. It's a double T with 5 strands per leg, and one of them is debonded at 15 millimeter from the end. And the question is, please calculate the MR at 35 millimeter from the end, which means that at 35 millimeter after, for the 4 of them that are not debonded and the 5th one that's debonded at 15. So we calculate the development lengths, and we calculate the transfer lengths for both cases. And we know that the transfer lengths for the bonded and the development lengths for the bonded need to be double that as per code 813.3 12.9.2. That the bonded need double as much lengths to transfer and double as much less to develop. So essentially, a section that we need, which is to calculate the moment capacity at 65 millimeter, has to be calculated using these numbers here, and we end up with 1311 megapascal at that section. So that diagram here is very, very explaining what we just talked. The bonded transfer at 735, develop at 1959. The debonded double as much, and this here is the total FPR, the final value, and this here is the value at transfer. So the bonded strand is somewhere here, and the stress at that particular moment, 35 millimeter from the end, is somewhere here. Therefore, at 35 millimeter, that the bonded strand has not achieved yet the total strength that we are requiring or need to reach if all of them were bonded. All of them were bonded, I mean. So, saying that, we need to calculate T sub R. Essentially, we have 8 bonded strands arriving at 1823 megapascal, plus 2 debonded strands arriving at 1311. And in this case, phi p need to be reduced to 0.7, not 0.9 for the bonded strand as an added cautionary feature. We ended up with this value here, kilonewton, calculate A, and from A we calculate the total M sub R for that particular section, which is definitely less than the value that we had all the strands bonded from end to end. Deflection. I think most of you are familiar with these formulae here. That's been sitting in a code for ages. The roof, which does not connected to non-structural element. This is the immediate deflection due to specified live loads, L over 180. And if this for the floors, same thing, immediate deflection due to L360. And roof and floor, if they are connected to something that will be damaged by the long-term deflection, the deflection will be L over 480 for the extra deflection that will happen after attachment of that particular element that will be cracking due to deflection. So essentially, it's a long-term deflection and heavy load deflection. For long-term deflection, we know that they will have this formula here. S is a value or a function that a factor function of the time, and rho dash is the ratio of reinforcement in the compression. And therefore, if this here becomes 0, this value here, and we'll talk in 5 years, this value here becomes 3, which is the maximum long-term deflection amplification. And same thing happened for pre-stressing. The pre-stressing camber do pre-stressing is changed by time, as also the deflection changed by time. And for each and every case, we have a amplification factor that were already established in practice. Here are the factors that we established. Amplification factor for deflection downward due to limit way and release of pre-stress. This camber upwards. This is that composite with composite, and then the final deflection downwards applied to elastic deflection due to element mass release of pre-stress. This camber amplification factors, and these are for the superimposed dead load only. I'll go through an example real fast now. We have a pre-stress the camber upwards. We have self-weight deflection downwards. That gives me this value here, which is the total deflection. Actually, it's upwards at release. At erection, this value here needs to be multiplied by 1.8. That gives me the camber upward due to pre-stressing at erection. This here will give me the self-weight downwards, and therefore the resultant is still upwards. And add to that the superimposed dead load that we added, and it gives me this value total after erection. Once we reach the final, we jumped back. Okay, once you reach the final, the multiplier change values. So the pre-stressing multiplier become 2.45, the self-weight multiplier become 2.7, and this will be multiplying these values at 1. Here, these values at 1, and then add to that 3 times the superimposed loads, and then add to that the live loads, and this will be the final deflection of this whole thing at 5 years from now. Okay, shear and torsion is an example that we need to be part that we need to be very careful with, because it keeps changing. And nothing changed much from this 8.3.314 to 8.3.304. I will tell you exactly what has changed. Those are the three things that will change from the old code to the new codes. Beta does not need to be at any less than 0.05, and also the spacing of 600 millimeter minimum specified close to TNT can be waived if beta is determined from the detailed procedure, and therefore the accepted sub ZA can be taken as S minus 300. These are the only 3 items that are detected have changed from the old code to the new code. Okay, essential formula: V sub R has to be equal lower than F sub F. If R, if BC, if VS, if VP, and shall not be greater than this value here, including VP, of course. And essentially we calculate factor shear resistance of the concrete, V sub C, which is this value here, again the same one like it used to be. And we have 2 methods of calculating beta. Either we can, if we have some minimum transfer reinforcement in the section, we can have beta equal to 0.18. If we don't have that particular reinforcement, then beta in the simplified method can be calculated using this formula, where d sub v is the depth, the concrete depth of section and shear. And beta can be calculated by the aggregate size by replacing dV with SCE, and AG here is the aggregate size, and SCE is essentially the spacing, the crack spacing. And the general method, beta becomes a little bit more complicated because we introduce the strain of the concrete at the crack section, which is calculated using the same formula that we used before in the past. For due to pre-stressing, the factor shear due to pre-stressing, Vs is this value if we have the longitudinal axis to an angle alpha. If it's not, if alpha equal to 90, then this will be the requirement, the required reinforcements. And theta can be determined by the following methods. Theta is 42 for conditional line, with basically what kind of material, what kind of section we have, the thickness of the section, the width of the section, and so on, is somewhere between 42 to 65 degrees. And then general method theta is again related to the strain of the section at the crack. And on top of all that, we have to make sure that the reinforcement, the material reinforcement in the section will satisfy this formula here at different section at the closer to support. It's a single T, and it has the strands are depressed. Therefore, we have certain angle for the strands, and you calculate the uniform load, the uniform live load. You calculate VF and MF in a table. I don't think we have the table in the presentation, but in the book we have the table for each and every section. And we calculate dV. It's either 0.72 H or 0.9 D. And in this case, it turned out that 0.9 D is the governing one, the smaller one. And VP essentially is the force that will be added to the formula due to pre-stressing, the vertical component of the pre-stress, because of the fact that strands are dipped, so they have certain angle. And once the strands are dipped, we generate VP, and then after that we check small v sub f, which is the fact that this value here. Make sure that it's less than 0.25, otherwise the section will not be adequate. Then in that particular section at 8 meter, we have, just give me one example, at 8 meter, we calculate the strain. And once you calculate the strain, we go to the next step. One thing about the strain, the strains they have limits. They cannot be less than 0.008 or greater than 0.03, of course. So this here is not less than minus 0.008, and at the same time is not greater than 0.03. So this strand stays as is. And we determine theta and beta based on the detailed formulae. And once we arrive at theta and beta, we calculate V sub S. If we have the book with you, it's not a bad idea to look at that table. Essentially, the table will give you V and F in every section. Will give you theta and beta in every section. Will give you the strain in every section, and therefore it will essentially tell you how to generate, how to plot that curve here, which is representing V sub C plus V sub P, as opposed to the straight line, which is V sub F, which goes flat here, and the end along the length equal to D sub V. You find out that there is a section here that needs some reinforcement. This area here needs some shear reinforcement, in addition to this area here that will need some shear reinforcement. However, this part doesn't, and obviously at the end, close to the mid span, we don't need that. So that will give you how we calculate that reinforcement. We're having 10M at 2 legs. V sub S, the formula just passed by it. Theta is 27.6. we calculate AV over, okay, we calculate how S would be. S to find out that S is 1429 by calculations, which is way higher than the amount that's minimum by codes, which is 600. Therefore, we have to reduce that spacing to 600. That's after that, actually, or they can be 0.7 dV. We find out that not 600 actually can be, it should be 529. So we agree on 500. So we have three values: one by calculations, one by this condition, and the other one by this condition. And each one of them gave us different numbers. So since we arrived at 529, we say we might as well make it 500. That would be the spacing of the stirrups. Last thing we check whether FR is larger than FT that needed at that particular section at 8 meters, and we find out that they are. And this is a table here that will give you section 1 to 12, calculation of FIT, calculation of F sub R. We'll find out that you're all covered, so you don't need any addition to the already provided longitudinal reinforcement for given there for flexural consideration. The next example is an example for for hollowcore. We're going through the same thing real fast, but we find out for that particular example, last time we tried to play with it a little bit. We tried to push as much as we can to make it safe, but this year we decided to keep it the way it is and make it unsafe in this area. The reason why make it unsafe in this area, because we believe as a community of precaster and precast engineers that the hollowcore need to be treated differently in the code, and the hollowcore as a component is in reality should have higher capacity and high strengths than those produced or generated for regular sections, whether they are pre-stressed or not pre-stressed. The research made recently or in the past 5-10 years that basically support this theory. However, A23.3 do not believe that yet. We have an argument with them for the time being with our representative there and the other people. And in the future, I believe that we would have special treatment in shear for hollowcore. And this is the reason why we decided to keep this example shown this way as unsafe without showing any reinforcements, because we don't put shear reinforcement hollowcore as a rule. Shear and torsion, that's nothing changed much here. We had the two acting together, shear and torsion. Next, please. These are the introductory that you can see in the book. For torsion, first thing we do is to calculate the critical torsion value of the section, the same formula that we had before. And if this critical torsion value is larger than is 0.25 of that value if the T sub F, that applied torsional value on the section is less than 0.25 T sub T critical, then no check of torsion is needed. So torsion is safe. If it's more than torsion is unsafe, we have to add it to our plates and check it with the shear. Reinforcement section is subject to combined shear and torsion. Essentially, for basically these are the three lines that need to be taken care of. This here for sections that have shear and torsion together. This is the crack. This is the formula here to make sure that the section will not crush or crack or crumble. This is the very second check. The first check is to check whether the torsion needs to be checked or not. If the section needs to be checked, then you go through the next step, which is to check the value of if the section will crush or not. And if the section will crush, then we have to change the dimension of the section from scratch. If section will not crush and that limit is achieved, then we keep going. After that, we'll keep going. We essentially change the formula that we calculate the strain epsilon x from the one that we use for shear to this one here, taking into account the effect of the torsion, and also the shear reinforcement shall be proportional to the requirement of this. But in this case, instead of having VF minus 0.5 F VS minus VP, would have a new formula taking into account the effect of the torsion. So essentially, these two formulae would be used, one to calculate the strain in the section cracked, and the one to calculate the requirements if we need reinforcement for the section under torsion. Example, LT section in a parking garage or a spandrel, and we have all the loads here, and we have four 13 millimeter low lax strands here, and we have 4 number 20 bar as well. So we have strands and bars in the same section. And what we need to know is what kind of shear and torsion requirements need to be designed for that strand, for that spandrel. This is new and changed. This section has been, this example have been revised from last time. So last time we did it in a fast way, and it wasn't that correct. But this one here is done the proper way. Essentially, we have also again sections that we have to go. Number one, we need to know whether minimum reinforcement has been achieved. We find that minimum reinforcement is achieved. This step number one for design, and we know that we need to know that that 1.2 critical is less than M sub R, and therefore after that we go to the minimum reinforcement for shear. We found out we covered that too. Then we go to the torsion effect. Torsion effect, we calculate the T crack, and T critical I mean, and we found that our torsion T sub F is larger than 0.2 F crack. T critical, then we need to check the torsion. The parameters we have is D sub V. We find that D sub V is this much at minimum, and then obviously we have to calculate the ACH, which is essentially the section of the spandrel inside that stirrup after getting rid of the cover of concrete cover. So that's why the 138 is essentially the concrete cover, the concrete lift inside the stirrup from the 200 widths. This here is the concrete left inside the stirrup from the total width of 1875, and they give us this number. And then after that, we calculate the parameter of the stirrup, and this A sub O is actually 85% of ACH. Next step is to calculate the strand. Then the strain in that particular section, we're starting at section 1600, zone 1, calculate the strain. Then when to calculate the strain, you calculate theta and beta, and then you calculate VC using this formula that has torsional effect here. Remember, we said that we need to use the special formula that has torsional effect in it. You calculate beta and theta, and then you calculate V sub C. And then from V sub C, you calculate the required reinforcement and find out the required stirrups are essentially, we need a stirrup every 300 as opposed to 600, because once the T sub F is larger than 0.25 TR, the stirrup spacing has to be halved as per the code requirement now. So the 600 we arrived here, which is the maximum allowed, it has to be divided by 3. And this is essentially the moment diagram, B diagram, TF diagram, and this here is the F sub C, and this here is the F sub FT that has the formula for torsion in it, and we found out that we are all safe 100%. Next. And this here is the reinforcement that needed, and make sure that all the stirrups are 135-degree tied as opposed to the 90 degrees. This is a condition in the code for stirrups supporting or resisting torsion. Okay, we'll go through this real fast. This we don't need to have much of that. Next, this is the columns now. We say that we pre-stress column for one reason, because sometimes we have columns that long, and even though the pre-stressing the columns will take away some of the capacity, however, it's sometimes when you need that length of a column, handling and shipping becomes a problem, and this pre-stressing the column becomes a necessity, even though it takes away some of the capacity, but that can be achieved easily by adding more mild reinforcement or increasing the F prime C. Piles, have quite a bit of piled produced in this country, the octagonal and circular, and they all pre-stressed, and we have the way to design them easily in the code and also in our book. Okay, handling and consideration. Obviously, at stripping, you need to make sure that you multiply the weight of the element by a factor, magnification factor, to make up for the fact that when you strip, there is certain suction on the piece that will increase the force that developed to the support points. And this formula here, or this table here, is very important, depending on what kind of material you're using, what kind of surface that you are achieving. And obviously, everybody knows what I'm talking about here. This is a standard location for picking points, depending on the fact that whether the section is prismatic or not. If it's not prismatic and has holes in it, or has doors, or has certain different section thickness, then we end up with a problem, because we need to make sure that these points essentially coincide with the CG of the element. So we need to calculate the CG in these cases, not just use this formula. Multi-wise panels, this is very high item now. Like you can see, there's so many types: non-prestressed, non-composite, and non-bearing, and purely architectural, smaller size, and you see them in buildings all the time. Small architectural type, non-prestressed, non-composite, but bearing. We see that all the time, like in the low-rise box buildings. And when they are high rise like this, like 40 feet high or 50 feet high, they have to be pre-stressed, and they have to be composite. So pre-stressed composites are non-bearing exterior wall in box buildings, like this one here. Also pre-stressed composite and bearing, as mentioned, or pre-stressed component, and sometimes we use them as shear wall in real building and high-rise building, shear walls. And so it can be bearing, can be shear, can be non-bearing and shear. There are so many different varieties of them, and there are so many different uses, and now it's even being used interiorly as interior shear wall and exterior shear wall in a high-rise building. And essentially, we prefer the pre-stressed, and we prefer the composite section to composite ones, because they give us more capacity and better structural behavior. That's it. Thank you very much.
Okay, great. Thank you for your presentation, Medhat. And everyone, please mark your calendars for the upcoming webinar presentations. The next one for Chapter 4, Design of Connections, will be held Thursday, July 19th at the same time, so 1 p.m. Eastern. And all of the other presentation dates are posted there on your screen. And you can register online at cpci.ca. I would like to also thank our Design Manual webinar series sponsors once again for their support. So BASF, JVI Inc., MCM Industrial Consultants, and Ultraspan. Okay, so at this time I'd like to open it up for questions. If you have any questions for our speaker, you can type it in the Q&A section that's on your screen, and I will turn it over to Medhat again.
Thank you. I can read it now. A question about shear. If I model the structure using a structural analysis tool, in this case I am using S-frame, the analysis shows shear force that is greater than the shear capacity of the concrete. This SCA states that the shear code does not have to be checked if A, B, and C are met. In any case, in many cases, they are all met. So I technically do not have to check what do I make of this. If you model a structure using the structure frame model, the analysis shows that the shear force that is greater than the shear using S frame. The analysis shows a shear force that is greater than the shear capacity of this concrete. Say that the shear, you have to check the shear. You have to check it, regardless. Unfortunately, what you're saying, it happens sometime, but at any rate, as long as the analysis shows a shear force that's greater than the shear capacity of the concrete, you need to check the shear from scratch. That's unfortunately, you have to check the shear. If the even if the CSA A23.3 does not tell you that you don't have to, but if the analysis shows a shear force greater than the shear capacity, then something is not right here. You need to check the shear, regardless of the other condition that you mentioned. Thank you. Is there a special design consideration for the lifting? Oh, that's me. The special design for lifting lug itself with the anchor rather than the pickup points. Yes, and it's in the book. That particular, I didn't cover it in that seminar, that webinar portion, because we were really moving real fast. But that's also covered in the third chapter, chapter 3. When do you think A23.3 adjust shear capacity for hollowcore slabs? It's in the middle of it. They usually have 5-year cycle. If they have new edition coming in 5 years, which will be this year, 18 or 19. Next year, I believe, we'll have the answer by then. So we have another year or so. I know that this time we're going to go for 10-year cycle, but I know at the same time that they're going to have some kind of revised A23.3.314 next year. So in that particular revised A23.3.314 version, we should see that adjustment. Another one, what are the most popular multi-waste panel used? I believe it is the prestressed composite section, used highly as a structural element, shear wall, bearing wall, and also non-bearing but shear wall, in high rises and in commercial area. These are the most famous and most used. Last one. What is the advantage of debonding strands in simple span? Obviously, you should know that once you bond the strands at simple span at closer to supports, you make sure that your stresses at transfer or before fully achieving the full load, your top fiber stresses do not get exceeded due to excessive pre-stressing force when there's no load coming on the other side in terms of dead load or live load to overcome that. So sometimes you like to debond the strands at both ends to make sure that the stress conditions are achieved, even though it might affect the overall stress value of the beam or the slab at midspan. However, this can be played with to make sure that it's working by adding extra strands or by adding mild reinforcements. Is there a difference between the design of the anchor zone of the post-tension thread bars and pre-stressed strands? Yes, definitely there is. And unfortunately, we don't have time to cover the post-tensioning portion, but yes, there is a difference. Oh, I need to do that. Is there a difference between the design of the anchor zone of the post-tension thread bars and the pre-stressed strand? Yes, there's differently there is. And we didn't cover the post-tension in the webinar here, but if you go to the book, you'll find the difference very clear. Thank you.
Okay, great. That concludes the Q&A session and the presentation for today. Thank you again for joining us, and thank you, of course, to our presenter, Medhat. We hope that you enjoyed the webinar presentation, and if you have any additional questions for CPCI or for our presenter, you can contact us by email at info@cpci.ca. So thank you, everyone, and have a great afternoon.